It's my pleasure to introduce the first speaker of today. Before I'll do so, I just wanted to quickly remind everybody of the format. We'll have two lectures. Again, they're both recorded, except for the Q&A session afterwards, for which we'll turn the recording off. The first speaker of this morning is Tom Heinsheimer from the Aerospace Corporation. He started out with a Bachelor in Science in Electrical Engineering from MIT and a PhD in Atmospheric Physics from the University of Paris. And he has had a long and distinguished career during which he was involved in a lot of interesting projects, of which I'm just going to give you a few examples here. For example, he was the project scientist in the Planetary Society's Mars rover tests in Death Valley, and also in some previous tests in the former Soviet Union. He has worked at the National Center for Scientific Research in France, in Paris, on rocket and balloon projects. Among others, he was also a member of the Mercury Atlas program staff, and now he's at the Aerospace Corporation, and today he's going to talk about the Solar Gravity Lens, which is a cool project that is also based on multiple small spacecraft. So please, Tom, and help me welcome Tom Heinsheimer.
Thanks very much for the introduction. As you know, the first speaker is the setup speaker for the main speaker, as in all jazz clubs. So the real action will be when Dave Murrow speaks. The other thing I have to announce to everybody is, since you've been working all night and doing all kind of things, if you nod off in this, you get a pass. It's okay. No one's going to say, "How come you're asleep?" It's okay. You can catch up later. Next week, you can watch this on the website or not. What I'm going to talk about is a project that may be even further out in time than the project that you are working on today, which is taking a whole bunch of CubeSats, which seem to be the in thing these days. Before that, I should introduce my cohort and partner, Henry Helvagian. Henry, if you'd stand up and say hello. Henry is one of the guiding geniuses behind this, working with Slava Turyashev at JPL, who also sends his regards, but he's heard this speech. So essentially what we're saying is there's been an awful lot done in looking at the solar system, and you're going to make further contributions. But in our kind of cynical view, aside from your project, we've been there and done that, and what we want to do is see if we can use the technology that's being developed in order to collect images of extra solar planets. Now, if you want to take an image of a planet that's orbiting around a remote star, there are really two ways to do it. You could go there. Problem of going there is F equals ma. It takes a long time. Stars out to 10, 20, or 100 light years, you got a problem. Or you could take advantage of our friend Einstein, who says that if you go out to the solar focal point, because light is bending as it comes around the sun, that it comes to a focal area, and if you went there and looked back, you should see what we call the Einstein ring. This is a Hubble image of an Einstein ring created by a galaxy. We're talking about an Einstein ring created by a star or a planet, which is much smaller. And if you went there, you could image this and reconstruct the image of the planet. Well, result of that is we put together some science papers with a whole bunch of people. As the project advances, I'm sure that some of you might be interested in participating. We've got about 50, 60 years of science papers to write about this, so feel free to get on board at your convenience. Here's how it starts. Yep, it's easy enough. Nothing to it. Light bends, and if light bends, it has to come together at some point out there. That would allow you to create a telescope, a virtual telescope, where we use the sun as one of the focal elements. And it looks like this. So way out here, at some distance, 10 or 100 light years, is a star. And it's got one or more planets orbiting around it. The light comes past the sun and is focused on a point which is actually a line. This is the solar gravity focal line. And it's a line because as light comes past the sun at ever increasing distance from the sun, it will be focused at places further and further along the line. So the trick now is to get a spacecraft to fly to this point and then fly along this line, looking backward and collecting the data and putting it together, sending it back to Earth, and on Earth, then you can reconstruct the image. Now, where do you want to go? This is a log plot, which of course you'll recognize instantly. And your target is here, and our target is Voyager's here, and we want to go there. So this point where we start to collect data is 550 astronomical units out. But, and you say, yeah, it's a big number. Yeah, but it's only 4 light days. So it just depends on your use of terminology and your units. 4 light days is not too bad, but you have to get there. So how are we going to do that? First, we are going to launch. The essence of this thing is that the spacecraft have to be small. They have to be small, they have to be cheap, and you have to have an architecture where everybody can be a player. So we have a system where we want to launch hundreds of these small spacecraft over several decades, and that makes each one of these spacecraft very cheap. And if you can launch them cooperatively with a bunch of launchers that are going anyway, so you get more or less a free ride, you can drive the total cost of this mission down. Because one of the things we're finding, and I'm sure you find that too in your study, is that these gigantic spacecraft that cost billions of dollars, take a long time to develop, and all of the risk is involved in a single flight and a single spacecraft and a single mission, have a disadvantage as compared with a new technology where you can spread the risk, launch a whole bunch of small spacecraft. If you lose half of them along the way, you still have a mission. And you can get a lot of people to pay for it. You don't have to have a gigantic NASA funding activity through Congress and all of that over many years. You can allow anybody who wants to contribute a spacecraft to this mission to do so. Our job would be to generate the specs and then let everybody fill the manifest over time as any way they want to. We would launch these small payloads into space and then equip them with a solar sail arrangement, which is our principal means of transportation. Here's what the solar sail, one look at what a solar sail might do. Now, how does it work? You first have to remember that in order to get out there to 550 AU, you got to be flying pretty fast, or otherwise, of course, it takes forever. So our model is to be flying at something like 25 AU per year, which is about 100 kilometers per second. So we've got to exit the solar system at 100 kilometers per second. The way to do that is you use the solar sail arrangement to spiral down to a perigee at the sun, to the perihelion. And at the perihelion point, you use the solar sail arrangement to accelerate to 100 kilometers per second, which means you have to have a very accurate ejection state vector so that you are exactly at the right speed and exactly in the right direction. Small errors in azimuth and elevation obviously are going to kill you. So there's an interesting problem of getting the acceleration and having a very precise state vector when you come out. You then use the deep space net and the solar sail to minimize the residual errors, dead reckon out to the solar gravity focal line, and then you use electric propulsion to work yourself into the proper line. Easy, right? Nothing to it. But again, do all that with an extremely small spacecraft. Because as the spacecraft gets bigger and bigger and more costly, the solar sail needed to get this velocity gets bigger and bigger, and eventually that solar sail arrangement gets so big that it's just not tenable from an engineering standpoint. So you get out there, then you have a whole fleet of these spacecraft that are flying over a long period of time, heading out into the cosmos. They deploy their solar sails, they pass close to the sun, they accelerate to 100 kilometers per second. And again, the idea is a whole bunch of them spread out over perhaps 10 years. So imagine you have several hundred of these spacecraft that are flying over about 10 years, which create what we call the string of pearls. Now, where do you want to go? Well, that is not our department, as Werner von Braun immortally said when he talked about launching rockets. He said, I launch rockets into the air. Where they land, it's not our department. Well, this is not our department, but still, in looking at all the data that we're now collecting from Kepler and from some of the other missions, there are attractive stars that have solar systems that are sort of Earth-like, because you don't want to go to all this trouble, and then when you get out there, you find out that you've only got gas giants. So this is not something where you want to look at gas giants, it's something where you want to look at Earth-like planets that could conceivably have some sign of intelligent life. So if, for instance, you flew this by Earth, you could theoretically see cities, you'd see bridges, you'd see roads, you would see clear evidence of some kind of civilized activity. And if you saw it on several planets in a given solar system, let's say you saw cities on Mars, then you'd get an idea of the state of the civilization that had created it, which might be worrisome. So the yellow are places which are of interest, and there's some places where they have multiple solar systems where you could be looking with one mission, you could be looking at a lot of planets. Our job is not to make that selection. So we have the whole scientific community would be working on this and would pick a few targets. Now, since we've got a distributed architecture, we don't have to pick one target, but each satellite, each of our CubeSats, once launched, can only go to one target. You can't reprogram it and decide, well, gee, we didn't like to go here, let's go somewhere else. But you could launch fleets of these spacecraft to any target that you want and do all of that concurrently. So you have an opportunity to broaden the scientific interest of this as a function of how many satellites you have, how much money you have, how much enthusiasm there is. So this is what the string of pearls looks like, a lot of small spacecraft, and the idea is drive down the cost, spread the money, gain the economics of scale, and allow lots of people to play. So different countries, spacefaring agencies, universities, anybody who wants to be a participant in this can play without having to get a $1 billion congressional authorization. So spreading the risk, spreading the cost, flying a lot of spacecraft, this is kind of the key to the idea, and not make it a one giant monolithic machine. And this is kind of the generic timeline. You launch a bunch of these pearls, you take 20, 25 years to transit, which you think is a long time, but if you look at Voyager, I mean, there are a lot of spacecraft that have been up there 25 years and are working perfectly well with technology that comes from the 1970s. So if we want to build something new using the present technology, there's no reason why they shouldn't last as long as is necessary. Then they get out there and they have a data collection interval, and as they fly out, each one of these observing spacecraft is sending data back. We put the whole thing together in some computers that will be probably right here. One of the interesting problems is that you got to get there very precisely because it's far away. The target is 550 AU out, but it's only a few kilometers. The focal line itself is only a couple of kilometers thick. So you got to be precise. You got to take care of errors. For example, you remember the way this works is you have a star over here, you got the sun here, and the light is coming from the star to this point. Well, one of the problems is that the sun is, of course, not stable in celestial space, because the sun is orbiting around the barycenter of the solar system. And this is kind of how the sun is meandering around. So there's a lot of motion that has to be compensated for. Luckily, it's well known, it's easy to predict. So we can say, all right, if we launched on a particular day, we'll arrive at a particular day, the sun will be in a particular place. So the motion of the sun between the launch time and the arrival time is not the problem, because we're going to aim for where it's going to be when we get there. The problem is that the solar focal line is going to be wobbling around following this kind of motion. So we have to have enough delta V on board to compensate for it. Luckily, though this distance, as you can see, is large, here's the sun, so we're talking about something like 1 million kilometers. We have a lot of time. So if you punch the numbers, it turns out that numbers of less than 10 meters per second per year is enough for the spacecraft to stay on the line. Then you've got to take care of uncertainties, drifts, errors, all this kind of stuff. But we've got to do everything we can to drive the delta V needed to do the mission down to the absolute minimum possible, because delta V is a fuel driver. Fuel driver is a weight driver. As weight starts to go up, things start to spiral out of control. Weight goes up, then the solar sail goes up, and the thing becomes untenable. So we've got to keep it very small, keep these errors under control. An interesting feature of the Einstein ring is what we call the plate scale. Because of the focal nature of the imagery, the size of when you're there looking at a solar system, an exosolar system, the size of that solar system is compressed by the plate scale, which is the ratio of the distance to the star with respect to the distance to the focal line. And so that's a compression for a typical, if you take the focal line is out at 4 light days and the star is out at, let's say, 100 light years, that's a factor of 10 to the 4th. So this image of the solar system is compressed by a factor of 10 to the 4th, which means that if you're out there, you could look at a lot with a single spacecraft and a small amount of motion. You can look at an entire solar system. You're not just looking at one object. So you can look at every planet, you can look at moons of planets, you can look at any object that might be of interest to you is within reach as you fly along the solar gravity line. And this is what it would look like if you were on the Earth. If you're on the Earth, in an Earth solar system, you can see that if you fly along, the red line is the focal line of the exostar. The planets orbiting around the star are going to be moving back and forth, but these numbers in kilometers are not millions of kilometers. They're the actual distance as seen by the object divided by 10 to the 4th. So you can see here over the period of a year that if you just stay on the line of the star, the planets will come by, and then you can just, with a little bit of delta V, you can follow them. And you want to be able to collect data from the planets when they're in a good position with respect to the star. So the illumination, there's a problem of the illumination of the planet and the interference from the star itself. Again, the beauty of having 100 or so instruments all working at the same time, because a different instrument, one of them might be looking here, another one might be looking there, and so on. So you can make these instruments dance around depending on how clever your ConOps is to gather the best data under the best viewing conditions for every single planet in the solar system. Some of the interesting challenge is going to be handled by some future machine learning and AI system. You got to know where you are. You've got to have systems that learn as you go along, because when you're 4 light days out, you're not going to be able to do any kind of instantaneous. It's the same problem that you have on your project, that it's out there far enough that when it gets into trouble or has any kind of problem, it's going to have to automatically correct and change the mission to compensate for local circumstances. One of the real problems that we have, I think that's unique to ours, is we fly around in order to get this 100 kilometers per second, and we're flying in a very complicated environment. You've got the sun, you're in very close, you've got a dynamic sun which is changing as a function of time and as a function of how you move around. And so in order to get the precise exit state vector, you're probably going to have to reprogram the mission every delta t, we don't know what that delta t is, depending on circumstances. You'll observe where you are, you'll observe the condition of the solar sail, you'll observe the condition of the payload, you'll observe the forces and pressures that are on it, and then you'll recompute the mission in order to get to the endpoint that you want. So we have kind of a very interesting challenge of the combination of technology, of the mechanics of the device, with the artificial intelligence channel of using those mechanics in a proper way. What if one of those solar sails fails? What if you get a little too close and things start to overheat and you have to move back? All of this is going to have to be sorted out in real time. And then when you get done and you come out with some kind of an error, you're going to transmit all that data back to Earth so that the next spacecraft that goes in has the advantage of what you've learned. If you fly several hundred of these things through this passage, presumably over time, you're going to minimize the losses, minimize the errors, and take advantage of technology insertion over, let's say, the 20-year period that you're launching these spacecraft. So it will need a lot of AI capability that is presently being developed. And what's nice is we've already got some software, some hardware that looks like it's going to be small enough and capable enough to do this job, but whether you can really do it in this very dynamic and at present uncertain environment is an interesting question. There are a lot of projects that are going on. One of the things that I'm sure you're doing as well is taking advantage of concurrent projects. If you were all on your own and had to develop all this by yourself, you'd never get there. But in the case of the artificial intelligence, hardware, software, and ConOps, there are all kinds of things happening. DARPA's working on it, JPL's working on it, various NASA centers, a lot of work being done in industry. So we've got to reach out to a lot of people, take advantage of all of this, and integrate this into a package so that we can allocate maybe 200 or 300 grams of total spacecraft weight to solve this problem. Another interesting thing is if you're out there, as in many space systems, like if you want to go to Mars. If you wanted to go to Mars, if you have a manned mission to Mars, you need a lot of mass for a lot of different functions. But a lot of that mass does not have to be used at the same time. It could be repurposed. You could reduce the total mass that you need in the system if you could repurpose some of the equipment, some of the structure, some of the instruments. And part of this study is to see how can you repurpose things like the solar sail, which starts out being used in order to give you propulsion, to do other things, like acting as a communications, acting as a sensor, acting as a star shade. So anything you can do as you're flying along to take your system apart, reconfigure it, and change the functionality of the equipment allows you, again, to dramatically reduce weight. And reducing weight is the absolute key to the whole game. So this is kind of the summary statement that came out of NIAC, Phase 2. We have a NIAC Phase 2 proposal. The way NIAC works is you have to have an idea that is crazy but not insane. It's kind of a difficult distinction to make, but they get a lot of NIAC proposals. And Henry is our expert in threading that needle very successfully, thank you. In phase one, I think we were able to show under the leadership of JPL that we had a concept that was credible, and the basic credibility involved two things. First, from the science standpoint, which was the work principally done by Slava Tereshev, that the ring existed, that the photons were collectible, and that the collected photons were of such a nature that you could put them together using various mathematical constructs to create an image. So if in theory you could, if you suspend belief, you're out there collecting the data, can that data be actually converted into something useful, which would be an image? We're talking about something like a 10-kilometer pixel of an exoplanet. So you think of the Earth, think about 10 kilometers, you'd have a pretty good idea of what was going on. You'd see continents, you'd see oceans, you'd see large human-created structures, you'd certainly be able to tell the difference between an Earth that was influenced by advanced civilization and one that was in the dinosaur age, given that the dinosaurs weren't building too many things. So phase one was okay, and then from the scientific standpoint. Then the question was the technology. So one of the things we did was we broke away from the one gigantic spacecraft and into the string of pearls concept. And that's something we recommend to you, because what you saw in the last Mars exploration with InSight was you had one large spacecraft, but you had two follower spacecraft, small CubeSats. And I think, and I think Henry thinks, we think that the future of space exploration is going more and more to entrusting core missions to ever smaller distributed spacecraft. So in this case, they had two. They worked perfectly well. They went along to Mars. They did exactly what they were supposed to do and significantly enhanced the mission. But they were there to enhance the mission. In our case, it is the mission. So we think over time there's going to be a change in the paradigm from big spacecraft to small spacecraft, and I think that's one of the things that interested the NIAC evaluators, and that we won the NIAC 2 award based on these two things: the scientific credibility of the mission and the technical feasibility by the string of pearls approach. That got us into NIAC 2. We're in the middle of the NIAC 2 phase. It's a 2-year phase, and it's a $500,000 award from NASA. And from there, we hope to see some kind of asymptotically, exponentially rather rising funding. The NIAC 3 is likely to be something in the order of 2 or 3 million, and we will be competing for that next year and trying to push this thing along. And of course, we look forward to a much bigger team, lots of scientists, lots of technologists, lots of interactions. We've got a group at, if I may mention it, Texas A&M, who's working on this and doing a graduate project. We expect to hear from them. We're going to be putting some of our young people in on the project this summer at Aerospace Corporation. So this is a wide open, non-proprietary, something where we're actively proselytizing people who are interested in this thing and want to participate, and we would welcome you on board. And with that, Henry and I will be happy to answer questions to anyone who's still awake.